Hello, am I audible? Yeah, good afternoon to all. Welcome to the fifth week tutorial session of NPTEL course Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So the main lectures that professor has taken in this week should be based on hydrodynamic fully developed flow, laminar slug flow, and power law fluids. So we'll see a few numerical questions and derivations based on these topics. Basically, the hydrodynamic fully developed and the laminar slug flow. The power law fluids actually deals with non-viscous, non-Newtonian fluids, and actually that will give you their hydrodynamic the energy balance. They will be having a different kind of flow compared to that of a Newtonian flow, and their energy analysis will be giving a better, a more generalized form of Nusselt number. And based on that, when we put the corresponding uh, power law index, maybe n equal to 1 or n equal to 0 or n equal to infinity, we'll be getting corresponding Nusselt number. So n equal to 1 corresponds to a Newtonian fluid, and for uniform wall temperature, it will be 3.66. Correspondingly, the value for a slug flow when n is equal to n equal to infinity, it will be nearby 5.66, I guess. So that is the till power law fluids he has discussed in this week's lectures, and uh, so in this week's in the tutorial session, today's tutorial session, we'll see basically a few numerical type questions based on. So I beg your pardon, it was 5.78 for the 5.78 for the slug flow, n equal to infinity case at a constant wall temperature. So the variation would be from 3.66 to 5.78 for a uniform wall temperature when it moves from Newtonian to slug flow. In this week's lecture, we'll see a few numerical problems based on hydrodynamic fully developed flow and the laminar slug flow. Slug flow in the sense where the velocity will be uniform. And similarly, on the other side, there can be a combination of thermally fully developed and thermally developing as well. So basically, in the case of slug flow, we assume it to be uniform flow for the for hydrodynamic side, but it's thermally fully developed for the other side, for the thermal power relay case. But in the case of hydrodynamically fully developed flow, uh, that will be fully developed. The velocity will be of the flow through the tube will be having a parabolic profile, not a uniform profile as in the case of slug flow. So we'll see a few numerical problems. Look into the first problem. It is a slug flow based problem. Solid food is heated by flowing through a uh, parallel plate channel of spacing D. The plates are isothermal at T0 and the flow is fully developed. So it's a case of slug flow, that is not fully developed profile. It will be uniform profile, and but the thermal part is fully developed. The flow can be modeled as a slug with a longitudinal velocity u uniform across the channel. Attach a system of coordinates to the channel and determine the fully developed temperature profile and the longitudinal variation of the mean temperature. Show that the Nusselt number based on the hydrogen diameter is Nusselt number is equal to pi squared. So look into the problem. I'll try to solve. I'll give you a couple of minutes to see what exactly the problem is and how we can tackle this. So we'll try to solve this problem. This is a case of a slug flow. So this is an application of the slug flow where the fluid flow is considered to be a uniform velocity flow, but it's fully thermally developed. And we have to actually, this is similar to that of the problems that we have seen in the previous week. Here we have to determine the fully developed temperature profile and the longitudinal variation of the mean temperature, T bulk mean temperatures, then we have to show that the Nusselt number based on the hydraulic diameter is pi squared. So in this case, we first of all draw this diagram. So this dimension is given as D, and the flow velocity is U, uniform velocity U, and throughout the velocity will be U. And it's given that the wall temperature is a constant at isothermal T0, and you can assume this to be the x direction and this to be the y direction. So it's a parallel plate channel. So I beg your pardon, that not the diameter, it's a parallel plate channels width between the channels that is given as V. So in this case, this is half d by 2, and this is minus d by 2 if you place this as a center. So this will be the coordinate 0, 0. For this case, we will start from the basics. So we assume a control volume where the heat flux is Q double bar. So we start from the basics first step. We have to calculate the variation of the mean temperature. So we can write the variation of mean temperature with respect to x, and dTm divided by dx. This we can get from the energy balance of the control volume. So that is equal to dTm divided by dx. We have to determine. So for this control volume, heat flux, the total energy would be written as Q double dash is equal to the heat flux multiplied by the area which is perpendicular to the heat flux. That is in the plane of the paper. We can assume this channel extends to a length L. So we can assume that length multiplied by 2 times the dx. So we can assume this dimension to be that of a dx. So dx into this direction will be giving you L. So that will be the area through which the heat flux happens. So that will be equal to the enthalpy change of the solid food particle that flows through. So that is equal to hx plus dx minus hx. So that can be written as rho into velocity into Cp. So this we can assume this to be that of an incompressible fluid. So the enthalpy change could be written in terms of the actual enthalpy change could be written in terms of the temperature change enthalpy, and pressure doesn't come into picture here. So it is equal to rho UCP into the volume. So that is L multiplied by rho into area. So that is equal to rho into U into Cp into area. So that is L into this dimension, that is D multiplied by dTm. So this is the rho into velocity multiplied by L into T will be area. So that will be mass multiplied by Cp into T into Tm. So solving this, we'll get dTm by dx is equal to 2 heat flux divided by rho U Cp into D. So that is the first. Now, so you do not know. So if you are to determine the longitudinal variation of the mean temperature, you have actually got an equation that relates this variation with respect to Q double dot. But you do not know the value of the heat flux. So that is an unknown. So U is a known, CP, rho is known. So we have to somehow determine the heat flux. So in the step 2, we can actually try to write heat flux is equal to the heat transfer coefficient into T wall temperature, isothermal wall temperature minus of bulk temperature. So this is equal to K into dou T by dou Y at Y is equal to D by 2 divided by T0 minus TR. That gives this H can be written as this one. So T flux could be written in the form of K into dou T by dou Y. Therefore, heating H is equal to therefore we can get the heat transfer coefficient as K dou T by dou Y at Y equal to D by 2 T0 minus T1. So that could be written as the second equation. So if you somehow calculate the value of the heat flux, heat transfer coefficient or the Nusselt number, we can back calculate the value of the dou Tm by dou X at the mean temperature variation. So that's the first part of this problem. Now we can slowly move into the second sections. So this is the case of a slug flow where therefore the velocity profile will be uniform throughout. So we need not solve the momentum equation in the x direction. So that is kind of a simplification for the problem. Now we will go to the basics of the energy equations. The original equation of the energy equation would be U dou T by dou X plus U dou T by dou Y is equal to alpha dou square T divided by dou X square plus dou square T divided by dou Y square. This is the energy equation without viscous dissipation and the heat generation term. So energy equation for steady non viscous dissipation and heat generation problem. You can do some kind of, this is actually the general form of the equation. We need to do some kind of scaling analysis to arrive at the reduced equation, which can be easy to work with. So we know that the variation, so we can scale it accordingly. From the continuity equation, we can actually, U and V are two different unknowns, right? U is equal to U itself. U will be scaled as the U direction velocity, which is uniform U. But so how we can scale the V? So scaling of V will be done as, scaling of V can be done as V from the continuity equation, from as in the continuity equation. So that is dou U by dou X plus dou V by dou Y equal to 0. So V will be of the form of U into Y direction, that is in the Y direction, it will be scaled as it's an internal flow. So it can be scaled as D, and X will be scaled as L, length in the or X direction, length in the X direction. So it can denote it by maybe some other term, maybe L. So this is different from this L which I have used. This is length in this direction. So that is, I can write it as with W. So that's why it could take the form W. So that I can avoid the confusion. So length is this direction in the flow direction. So based on that, we can get the scaling for V done. So substitute back here. Then and it's assumed that the flow is fully developed in it's thermally fully developed. So that means that the variation of the non-dimensional temperature could assume to be that of the CO. But we for the time being, what we do is that the variation of the So this is assumed to be that of a so what we could say is that V is approximately scaled as the scale of V will be of the order of U into D divided by L. So if we assume that the L is very much greater than D, so this is the case of parallel plates, and the dimension of this D is very much like less than that of the L. So we can consider if we assume like that, then V will be V will be very much less than that of U. Can get in the form of V. So we can assume V to be approximately equal to 0. Because of that, this will become equal to 0. Substituting back, we can get V to be approximately equal to 0. So reduced equation will take the form U dot T dx. U is a the velocity variation in U, but here it is a constant. U is the same. Then we have the other two terms, alpha into dou square T divided by dou x square plus dou square T divided by dou y square. So taking this alpha on the other side, you can write it as scaling analysis. So U alpha dou T by dou x. This dou T by dou x, we actually do not know the scale of dou T by dou x. If we have to reduce this energy equation, you have to use some kind of scale. For that, what we could do is that we could take the equation of dou T by m by dou x. This is one of the reasons, and we make an approximation that dou T by dou x will be of the range as that of dou T m by dou x. Is of the order of dou T m by dou x, and you can straight away substitute this to Q double dash rho UCP by D in there itself. Approximate the scale to be same as dot dTm by dx. So that is equal to so substituting the equation of dou Tm by dou x here, so that is equal to 2Q double dash divided by rho U Cp into D. This is the convection term. And how can we do dou Tm by dou x? Dou Tm by dou x could be same as that of dou by dou x of dou T by dou x. Dou T by dou x will be of the same order as that of this one, and x will be, you have to write x separately. So that can be 1 by x, that can be scaled as 2Q double dash divided by rho U Cp D. And this dou square T divided by dou y square, we do not have we do not have a scaling equation, and that can be corresponded to this one. So we could write as dou square T can be dou T can be written in the form of del T, the temperature difference in the y direction between the wall and the central mean temperature, and the y direction can be D squared. In order to show kind of an equivalence, what we could do is that we can take this delta T on the opposite side, and we'll try to simplify this equation once again based on the scaling. So what we could do, taking this delta T by D squared on the opposite side, this will become equal to U by alpha, and take this and expand this alpha as K by rho Cp. We can try to simplify some terms. So that will be 2Q double dash K divided by rho Cp into U D multiplied by D square divided by delta T So this will become equal to this K by rho Cp will get cancelled. So it will take the form 2Q double dash D divided by K into delta T. That will 2Q double dash uh, D divided by K into delta T. So this Q double dash D divided by T divided by K will be the heat transfer coefficient. Q double dash divided by K delta T, that will be the heat transfer coefficient. So that will be equal to, I beg your pardon, Q double dash divided by delta T will be equal to the heat transfer coefficient. So 2HD divided by K. So that will be the form of the first term. The second term, so this term you are taking on the opposite side. So this term will be 1. And how will the other term behave? So that is equal to similar to that Q double dash divided by so this delta T divided by D squared. So there will be an H term and a D term on the top. So that should be 2HD divided by X will be there, this X term, and then rho Cp and U remains. So what we could do is that so we have to have some kind of equivalence. So here we in this particular equation, we do not know the scale of X. So if we can somehow scale X using some other method, we can actually remove that from the equation. So what we could do is that we can actually use we can actually use this equation dot t dtm by dx can be equal to dt by dx of the same order. Therefore, dt takes a form delta t and x takes a form x. What we are trying to do is that we will write x in that form of all other parameters. So we can denote it by 1. So we in order to scale x, what we could do is that I can write dt by dx is of the order of delta t from, so you can denote this by 1 and this by 2, this by 2. From 1, dt by dx will take the form delta t by x. So that is can be scaled as 2q double dash divided by rho u cp and rho u cp and d. Therefore, hex can be scaled as delta T rho U Cp D divided by 2Q double dash, and Q double dash divided by delta T can be written in the form of heat transfer coefficient. So, so that is rho U Cp D divided by 2H. So that will be the scaling of X. So what we could write is that the first term so the therefore equation 2 becomes left hand side remains the same 2ht by k, and you substitute x as this form. So substitute sub 3 into equation 2 becomes 2ht by k, and we instead of x we write to rho ucpd divided by 2h. So that's why the new equation by simplification will come as 4ht by k squared k divided by rho cp u d, the whole squared, and the last term will be 1. So the conduction, we could assume that the conduction in the y direction, the variation in the temperature will be significant compared to that of the, or the diffusion term in the y direction is significant compared to the x direction. So last term of dou square t divided by dou y squared, that will remain in this equation. So we can actually remove that statement. That's why we scale everything else with respect to that. But that is a heuristic based assumption, but we have to prove that. So that proving part can be done using the scaling analysis. So now we have a simplified equation for the x term, for the x direction conduction. So this is the term. So the second term we can actually do some kind of mathematical manipulation. So what we could write is that UD divided by alpha, K by rho CP is equal to alpha. UD divided by alpha will be the Peclet number term. So this will be, can be written as 4 HD by K into K by rho CP divided by UD, that is equal to 1 by Peclet number. 1 by Peclet number, the whole square. So the Peclet number uh, P is equal to UD divided by alpha. So it shows the relative so this is K by rho CP. This is diffusivity, thermal diffusivity of the material. UD actually shows the momentum, the convection term, the flow across it. So it's basically quite kind of convection to conduction. So once the value of the Peclet number is quite high, we can assume that convection dominates over the conduction, and we can neglect the conduction. So that's what it says. So for larger values of of Peclet number, that is when Peclet number greater than 1. So this particular term actually, the second term reduces to 0. So in that way, what we could do is that we can neglect the axial conduction, or neglect the conduction uh, along the axial along the flow direction. So that means that in the flow direction, only the convection term dominates. The conduction, the conduction is negligible, but there is conduction in the y direction. That is perpendicular to the flow towards the isothermal wall sides. So therefore, the simplified energy equation. So that means that this term can be the first term on the right hand side can be neglected. So simplified energy equation will become as U by alpha dou t by dou x is equal to dou square t divided by dou y square. So this is for the simplified energy equation for slug flow. So this is actually the energy equation that we will be using for the from this point onwards. Now the next step is we have to solve this energy equation, and then we have to determine the Nusselt number and the temperature profiles. So we have to actually, for this case of a constant wall temperature, we have to arrive at the generalized similarity temperature profile that based on the wall temperature, mean temperature, and the temperature at a location. And that can be actually a function of a similarity variable for the distance. That distance that we have, choosing the distance, similarity variable for the distance can be tricky. It needs a bit of ingenuity. So the generalized temperature profile could be written as theta, that is step 5, step 3, step 4, generalized temperature variable or similarity profile. Similarity temperature profile. So that can be a theta. So that theta can be written as T minus or wall temperature if it is assumed to be higher, T0 minus T minus T0 minus T mean temperature. So that can be the generalized temperature. So how will we actually get this as a function of, how will we show that this is a, we can denote it by maybe phi or something, phi or theta, either of them maybe for phi. So can be denoted by phi. So this is the variable. So this should be a function of the similarity variable for the distance. So how will we arrive at that in the first place? So for that, we take the Nusselt number order. We try to scale the Nusselt number, and using the scaling, we will actually get this to be a function of the similarity variable. So similarity variable, we do not know how to uh, arrive at a similarity variable for the distance. So we will be having several parameters, maybe the y direction distance, maybe y itself, and then corresponding some other constants are also there. So we will arrive at a similarity variable for the distance as well, and based on that, we will try to show that this similarity variable of the temperature varies only with respect to the similarity variable in the y direction. So we do not know at this point in time, we do not know the similarity variable in the y direction. So this is 5, can assume this will be 5. And we use a scaling for the Nusselt number. We know that the Nusselt number in this case varies from 1 to 10 somewhere. So Nusselt number can be of the order of, Nusselt number can be of the order of 1. So Nusselt number is, we have already calculated initially Nusselt number. For this particular case, Nusselt number will be is equal to hc by k. So characteristic dimension will also be there. So the characteristic for the this is parallel plate kind of a problem. So a characteristic length for this case of case can be written as 2 times the diameter, 2 times the distance between the channel. So 2d. So that's kind of easy. So what we could do is that we can actually get between the area and the perimeters, or that is equivalent to the cross-sectional area and the perimeters, or it can be equated to that of a volume and the surface areas. So 4 multiplied by the area divided by perimeter, that will give the characteristic dimension. So hydraulic diameter, it can be close to the hydraulic diameter as well. So that is equal to 2 times the this dimension of D. So Nusselt number can be written as h into 2d divided by k, that is approximately equal to 1. H can be written as in terms of q double dash and other terms. So it will be 2d divided by k into q double dash divided by t0 minus t mean, that is approximately equal to 1. Then this q double dash can be again written in the form of k dot t by dot x. So that is can do some kind of manipulation. So that is 2d divided by k into t dou t by dou y at y is equal to t by 2 divided by t0 minus t mean. So that is equal to 2d k cancel dou by dou y at y is equal to dou by dou y at y is equal to d by 2, that is a var divided by t0 minus tm. Is approximately equal to 1. So that means that dou by dou y is of the order of t0 minus tm. So dou by dou y divided by t0 minus tm is of the order of uh, so this can be plus dou by dou y will be of order of t0 minus tm. It is a dou by dou y is of the order of t0 minus tm. So you'll do some kind of a we will do some kind of a manipulation here. So we can write dou by dou y at y equal to d by 2 divided by t0 minus tm is an order of so this is actually the variation with respect to the y direction, variation of the temperature with respect to the y direction. So this variation this actually varies with respect to since it's a fully developed flow. So we can say that the variation of this particular term in x direction, variation of the singularity variable in x direction is actually negligible. So because dou by dou y is of the order of the dou by dou y term, this this so there is this 2D term. So that 2D term also will go to the right hand side. So that will be 1 by 2D and this will be 1, right? So the dou t can be scaled as maybe t minus t0 minus t. So yeah, the T0 delta dou t can be scaled as T0 minus a temperature at a particular point divided by T0 minus T mean can be scaled as y can be scaled as y, so we can write it to be y divided by d. So this is of the order of y by d. So neglecting the constant terms. So in order to make it a bit more convenient, right, we can write it as y divided by d by 2. So based on that, what we can do is that this is a function of y divided by d by 2. So we can write as this is equal to t0 minus t. You should understand that we are doing this kind of an analysis only to arrive at a similarity profile for the y direction and try to equate with that of the temperature profile. So T0 minus T is a function of y d by 2 wholly. So integrate this and we'll get this is t0 minus t that it can get plus dou t by it can't actually do that straight away, right? So that's a kind of a confusion that had arisen. So this can't actually do this kind of a thing. So I try to uh, I understand that this can be a bit of confusing, but what I try to do was that I'm trying to arrive at a similarity equation that will be that will be actually comparing the temperature, dimensionless temperature with that of a dimensionless distance. So this is actually not right, kind of not right. So it should be actually dou t by dou y itself, dou t by dou y t by 2. So you can integrate it and you can say that t minus t divided by t0 minus t divided by t0 by m is a function of only d by 2. This can be a function of only d by 2 and because the value of this one, the variation, when you put t is equal to t0 and put y is equal to d by 2, you'll get the value to be 0. So that means that the constant term, what we'll be getting is equal to 0. So based on that, we can write this is f, uh, this f plus some constant term that is dependent upon the x. This since the dimensionless profile doesn't change with respect to x, so we can write it at some particular point c of x constant term uh, will be only dependent upon that particular constant, let's say into y d by 2. So we try to simplify that. This is equal to t0 minus t divided by t0 minus tm can be written as only a function of y d by 2. So this particular term c constant term will become equal to 0. So that's kind of a crude way of trying to show that the temperature profile, dimensionless temperature profile, is same as is depend only on the variable, bidirectional variable. Now we move and we try to show the variation of the temperatures. So we are on step number 5. So basically what we are trying to do is that we are trying to arrive at the Nusselt number. So for to calculate in the Nusselt number, we actually require we need to solve the mean temperature variation as well as the actual temperature variation with respect to x. With respect to x as well as with respect to y. So using those two, we can arrive at this Nusselt number y. So what we do is that we have this mean temperature variation dTm by dx. So can write dTm by dx is equal to 2q double dash divided by rho u cpd from the previous equation. We do some kind of a manipulation and write it in terms of heat transfer coefficient, that is dTm by dx is equal to in terms of heat transfer h divided by delta t. So that can be plus h into delta t, h into t0 minus t mean. So that is equal to h into t0 minus t mean divided by rho u cpd. So we have a formula. So what we try to do is that we try to arrive at we integrate this equation and get the temperature profile, mean temperature profile. So that is Tm divided by T0 minus Tm is equal to 2H divided by rho UCPD into dx. So integrating it in terms of a logarithmic profile and by putting the uh, temperature variation with respect to first one temperature and a second temperature, we can actually arrive at this value. And here So we need to actually we actually would require an initial temperature or the temperature at the inlet. So for the time being, we assume the temperature at the inlet average temperature is equal to T1, and the mean temperature at some other some other point is Tm. So solving this, we'll get ln of T0 minus Tm divided by T0 by T1, that is the initial temperature, is equal to minus of 2h rho u CPD, and x distance, this Tm at x distance, and this is x1 at the initial point. And we try to write it in terms of the in an exponential form. We can write T0 minus Tm is equal to T0 minus T1 e raised to minus of 2h divided by rho UCP into x2 minus x1. So this can be written in terms of Peclet number and Nusselt number. So we can write h, we can multiply and divide the numerator, multiply and divide this term by k, and then d as well. So it can be in the form of hd by k, that is h into 2d by k, that will be the Nusselt number. And similarly, the Peclet number will be u into 2d divided by u into 2d divided by alpha. So I beg your pardon, there was a confusion regarding the Peclet number. Peclet number is UD divided by alpha. So based on that, we'll get solving, we'll get e raised to minus of Nusselt number into Peclet number divided by d into x minus x1. So that will be the temperature profile equation. So this can be represented by equation 5. This can be represented by equation 5. Now the next step is to solve the energy equation to obtain the temperature profile. Solve the simplified energy equation, equation 4, to obtain the temperature profile. So what we have is T minus T0 divided by, so we just expand it, so that is equal to T minus T0 divided by T0 Tm into, is a function of phi of y by 2. We do not know the profile of the temperature right now. This function we do not know currently, and we know that u is equal to u for the uniform velocity. What we could do is that so this is the temperature profile currently we are having. So this is a similar from the similarity variable, and the u is equal to u from the slug. So we have this equation dou t by dou x is equal to 1 by alpha dou t by dou x is equal to dou square t divided by dou y square. So that is equation. So one not u by alpha. So u by alpha is equal to dou t by dou x and dou square t divided by dou y square. So we have to somehow write this dou t by dou x in terms of phi and the other terms. So phi is dependent only on y. So therefore dou t by dou x can be written as phi into dou tm by dou x, the variation dou tm by dou x, and this can be written as again dou tm by dou x. We know the temperature profile we have obtained from the energy balance, so that is h into T0 minus divided by rho UCPD. So we do some kind of a manipulation here as well. So that is Nusselt number into alpha, you just multiply it by d on the top and the bottom, as well as k here and there. We'll get Nusselt number. K is semiconductivity, so Nusselt number, and then one alpha term in the main T0 minus Tm, and you can arrive at this form by actually doing some kind of a manipulation. So this is nothing but mathematical simplification of this original equation in terms of dimensionless variables. So similarly, dou t by dou y can be written as dou t by dou y can be written as, you just differentiate this equation, so that is minus of T0 minus Tm into dou phi divided by dou y. Once again, you differentiate it to get the double differential. So that is minus of T0 by Tm into dou square divided by dou y square. Therefore, the original equation, we substitute these differential values. The original equation will become u by alpha phi Nusselt number divided by ud square alpha T0 minus Tm minus of T0 by Tm into dou square phi divided by dou y square. So what we are trying to do is we are arriving at the dimensionless values of the dimensionless energy equation. So that we'll try to simplify. We'll get phi into Nusselt number divided by T squared and is equal to minus of dou square divided by dou y square. So this is in terms of y. So what we can write is a eta as a dimensionless variable of y divided by d by 2. Therefore, dy is equal to d by 2 d eta. Therefore, phi into Nusselt number divided by t square is equal to minus of 4 by d square dou square phi divided by dou eta square. Substituting dou phi by dou y can become dou phi by dou eta into dou eta by dou y, and substituting the value of dou eta by dou y, that is equal to 2 by d, and we'll get this as 4 by d. Therefore, 4 by d square. Therefore, what we could write is minus of phi into Nusselt number divided by 4 is equal to phi double dash. Therefore, phi double dash plus 5 into Nusselt number divided by 4 is equal to 0. That is the final differential equation, and we try to solve this. This is a homogeneous equation. The right hand side there is 0. It's a constant, so it's kind of easy to solve this problem. So the left hand side, it is in the form of a double differential of phi double dash and 5, and Euler kind of a Euler. No, it's a normal differential equation. We can solve it. So by if we can write the double derivative as d squared and the first derivative as d, and the normally as a constant one. So what we could write is that is taking 5 out of it, d squared plus nu by 4 into 5 is equal to 0. Therefore, solving this differential equation, dou squared plus nu by 4 is equal to 0. We'll get phi is equal to c1 cos in the form of surds. So root of Nusselt number divided by 2, eta is the y dimension, y direction non-dimensional variable is eta. So this is phi double dash is with respect to eta plus c2 sine root of Nusselt number divided by 2 into eta, the form of surds. So when eta is equal to plus 1, phi will become equal to 0, and you will get one equation 0 equal to c1 cos root of nu divided by 2 plus c2 sine root of nu divided by 2. And similarly, we can differentiate this equation. So phi dash is equal to minus of c1 root of nu divided by 2 sine root of nu by 2 eta, substituting eta and plus C2 into root of nu divided by 2 cos of derivative of cos is minus sign and sine is cos. So root of nu divided by 2 into eta. So at eta is equal to 0, phi dash is equal to 0. That is another boundary condition. So phi is eta equal to 0 is y equal to 0. That is a middle point. So what we could see is that the temperature profile will be attaining a uniform value, or due to the symmetry condition, we can say that the variation of the dimensionless temperature profile with respect to the center line will be equal to 0. So substituting the value of eta is equal to 0 and phi dash is equal to 0, we get an equation 0 is equal to minus of C1 root of nu by 2 sine root of nu by 2 sine 0 is 0. So this term, first term is equal to 0 plus C2 C2 root of nu divided by 2 cos of 0 is 1. So what we could see is that C2 root of nu by 2 is equal to 0. That implies that C2 is equal to 0. So the second term goes out completely. Therefore, from the first equation, we can get C1, C2 is equal to 0. We can see C1 C1 cos root of nu divided by 2 equal to 0. C1 can't become equal to 0, then it will be a trivial solution. Therefore, root of Nusselt number divided by 2 cos root of Nusselt number divided by 2 is equal to 0. Therefore, the to get a realistic solution, we take the first realistic solution. We can't put we can put first realistic solution comes at pi by 2. So that will be equal to root of nu divided by 2 will be equal to pi by 2. That implies Nusselt number is equal to pi squared. So that is the first part of the problem, where we have actually tried to prove that the Nusselt number based on the hydraulic diameter is pi squared. So what we did was that we have to integrate the energy equation and do some kind of a manipulation to arrive at this equation. We arrived at the simplified energy equation, and then we have to actually write. We do not know the temperature scale, the variation of the temperature scale in the x direction. So we try to equate with that of the mean temperature variation, and based on that, mean temperature variation can be correlated to that of the Nusselt number through heat transfer coefficient, thermal conductivity, and the capacity dimension. Here is a hydraulic diameter. So based on that, we had actually arrived at we have actually arrived at the value of the Nusselt number. So that completes the first part of the problem. So we have solved this section of a Nusselt number. Now we have to actually arrive at the fully developed temperature profile and the longitudinal variation of the mean temperature. That is the second part of the problem. For the temperature profile, we have to we have to have the function. We need to know what exactly is the function that gives the temperature profile relation with respect to the d by 2. So what we could do is that from this analysis, what we could see is that phi, the temperature profile, is equal to C. Temperature profile is equal to the C into cos root of Nusselt number divided by 2 into eta. We do not know, still now, we do not know the value of the constant C1, right? So we have to find that constant and we'll get the temperature profile straight away. So that is equal to phi into C of cos pi by 2 eta. So in order to find the C1, we use heat flux equation that is equal to Q double dash is equal to minus K dou T by dou Y at Y is equal to D by 2. And what we could write is that Q dash is equal to H into T0 minus Tm, and K can be written as minus of K into T0 minus Tm into dou phi by dou Y. So that those two gets cancelled out, and we can write H is equal to so basically dou T by dou Y the cos will so when we differentiate this term, that will be equal to so it is so this heat flux is internal one. So the temperature can be written as so this can be written as H into T0 minus Tm is equal to minus of K into dou phi by dou Y into T0 minus Tm. So T0 minus Tm gets cancelled. So I beg your pardon, there's a minus it. So therefore, what we can write is H is equal to K into dou T by dou Y is equal to phi dash divided by D by 2. So I beg your pardon, it is dou phi by dou Y, and we put eta is equal to minus 1. So at Y is equal to minus D by 2, we try to solve this. So K into dou phi by dou Y into in terms of dou phi by dou eta, this term can be dou phi by dou eta into dou eta by dou Y. So at Y is equal to eta is equal to Y divided by D by 2 at dou eta by dou Y will be equal to minus 1 at this particular point. So that will be equal to H D divided by 2K is equal to phi dash into minus 1. So this is one equation, and substituting phi dash is equal to C1 minus of C1 sine into pi by 2 eta equal to minus 1. We can write HD by 2K is equal to minus of C1 into pi by 2 sine of pi by 2 into minus 1. So sine minus pi by 2 is equal to minus 1. That will get cancelled. That will be equal to plus terms of HT divided by you can write as H into 2D divided by 4K, some kind of a manipulation. So minus of C1 into D by 2 sine pi by 2 it will be plus. So it will be d by 2, I beg your pardon, it is pi by 2. It is pi by 2 into C1. So that is 10 to the plus h into 2d divided by k is Nusselt number divided by 4 is equal to C1 into pi by 2. So therefore C1 is equal to pi by 2. This is Nusselt number is equal to pi squared divided by 4 into 2 by pi, so that is equal to pi by 2. So C1 also will become equal to pi by 2. Therefore Q therefore phi can be written as the temperature profile phi can be written as pi by 2 into cos pi by 2 eta. So based on this, we can get the fully diluted temperature profile. Phi is equal to T0 minus T divided by T0 minus Tm is equal to pi by 2 cos pi by 2 eta. So this in terms of pure dimension values, dimension variable, so it will be equal to cos d by 2 into y divided by d by 2. So that is the very so based on this we can that is a very equation for the temperature profile. Now we need to get the value of the now from this one we can actually get the value of the so we have already determined the value of the mean temperature variation. So Tm the mean temperature variation T0 minus Tm could be written as T0 minus T1 at a point where the x dimension is x. We could write it as e raised to minus of nu divided by Peclet number into d into x minus x1. So we substitute that and we'll get the value of uh, the uh, the temperature profile, the actual temperature profile. So that will be equal to T0 minus T is equal to T0 minus T is equal to T0 minus T1. So T0 minus Tm is equal to T0 minus T1 at x equal to x1 into e raised to minus of Nusselt number divided by Peclet number into t into x minus x1. So that will be the the temperature profile multiplied by this particular value d by 2 into sorry d by 2 into there was some kind of color. This is pi by 2. So this is cos pi by 2 into y d by 2. So that is pi y divided by d. So that is equal to into pi by, and this is pi by 2 as well. So I made some mistake here. So it's pi by 2. So it's totally right. So while writing, I have wrongly written that as d is pi by 2. And this is also pi by 2. So which is pi by 2 into cos of pi y by d. So this is the final equation that gives the temperature profile. So we have already calculated the mean temperature profile, and now we have this equation as well. So the Nusselt number we have calculated phi squared, and the final equation is final temperature profile is this one. So that was a long problem trying to solve the Nusselt number based on the hydrodynamic diameter pi squared and the temperature profile. I generalized value of temperature profile by solving the energy equation, by solving the differential equation. Now we can look into the second problem, try to solve it, and I'll also try to solve it within a couple of minutes. So consider the heightened poisefully flow through a tube of radius r0. The flow is extremely viscous, so that the energy equation reduces to this form, where phi is the viscous dissipation term. Phi is equal to du by dr the whole square. Determine the temperature distribution inside the pipe subject to T is equal to T0 constant at R is equal to R0. Let Q be the total heat transfer rate through the pipe wall over a pipe length L. Prove that Q is equal to m dot P divided by rho, where m dot and delta P are the mass flow rate and the pressure drop over the length L. So it's a fully Hagen-Poiseuille flow. So we know the temperature profile will be of the form. The energy equation will be of the form K into 1 by R d by dr. This is the diffusion term, and this is the viscous dissipation term. So as a fluid flows through this tube, it tends to heat up due to the friction, and that is a viscous dissipation term, mu phi K by R d by dr R dt by dr is equal to mu du by plus mu du by dr the whole squared is equal to 0. So once the flow happens, the this uniform temperature T is equal to 0 at R is equal to 0. The diameter is R0, and the heat flux happens in this direction. So once once the fluid flows through, they will be heating up. And that is represented by the viscous dissipation. That needs to be that particular heat needs to be ejected out of the system, and that will be done by using the diffusion term, and there will be a heat flux Q double dash outside. So we need to prove that the Q, the total heat transfer through the pipe wall, that is Q double dash into the surface area of the pipe can be written in terms of the pressure, mass flow rate, and the pressure drop over the length L. So it's a tricky problem. We can try to solve it. So the boundary condition in this case is dt by dr is equal to 0 at r is equal to 0 due to the symmetry condition, and t is equal to t0 at r is equal to 0. And it's a Hagen-Poiseuille flow. So scan 2. So we can write u is equal to, from the parabolic velocity profile, I'm straight away writing it. It's already derived many times before in the lectures as well as in the previous tutorial session. U is equal to, sorry, in the lecture, 2 into u into 1 minus r divided by r0 the whole square. And from that, you can write the average velocity profile. U is equal to this one form of writing this, and the average velocity profile can be written in terms of the pressure gradient. So that is equal to r outer square divided by 8 mu into dp by dx. So minus 10. So this is from the Hagen-Poiseuille flow. Can be denoted by equation 3. This velocity profile and the mean velocity profile. So we should try to arrive at the temperature profile. So we have the u value. We have the du by dr. So we have the velocity profile straight away. So we can write du by dr from here. So that is dependent upon the r and r0. So based on that, we can arrive at the final temperature profile. So T minus T0 temperature with respect to the wall is equal to mu into u squared divided by k. This is a final equation. We can do the simplification mathematical calculation based by integrating them by providing the boundary condition at r is equal to 0 and r is equal to r0. Then the heat flux is equal to minus k dou T by dou r at r is equal to r0. So dou T by dou r, you differentiate with r equal to r0 and substitute. This will be 4 into r by r0, the whole cube. Minus of 4 into r by r0 whole cube. the first term will be a constant, but that is differentiating with respect to r, that will become equal to 0. So we'll get this as equal to 4 into mu u squared divided by r0. And this is average velocity, that's a constant, mu is a constant, r0 is a constant. So this heat flux is a constant. So the heat transfer rate is equal to q double dash into L into 2 pi r0. That's the surface area, perimeter into the length of the tube. So that is equal to 4 mu u squared divided by r0 into L into 2 pi r0. That is equal to 8 pi L mu into u squared. So we can write we can make some manipulation, and we can use the equation of the velocity, average velocity in terms of the pressure, and we can write q is equal to 8 pi L mu u into u, and you can be written as r0 squared divided by 8 mu minus of dp by dx. So pi into area into pi r squared into pi r squared, that is the cross-section area, multiplied by the velocity into rho, will give the mass flow rate. So what we could write is that pi into r0 squared into u. We can club pi r0 squared and u together, and then we can write, we can actually uh, this 8 mu will get cancelled, and only dou p by dou x remains along with L. So that is L into minus of dp by dx is the pressure line. So this can be written as mass flow rate divided by the density. And this is minus of dou p by dou x can be written as a pressure gradient. So P1 minus P2, that is equal to, can be scaled as the pressure gradient along the length multiplied by the length, assuming it to be a linear variation. So that gives Q is equal to m dot into delta P divided by rho. So we can get the flow rate. We can arrive at this heat transfer rate. Total heat transfer rate is equal to the mass flow rate multiplied by the pressure drop divided by rho. So here in this kind of a flow where the heat transfer is due to the viscous dissipation, the element that creates a that triggers a heat transfer is the viscous dissipation. So when the viscous dissipation is equal, uh, when the viscous dissipation is present, that will be taken by the conduction term or the diffusion term, and then that will be ejected out of the system as a heat. So we can assume that the heat transfer is actually dependent upon the friction that is in term that also creates a pressure drop. So we can try to equate the heat transfer with the pressure drop using this equation. So these kind of only these kind of a problems, specific problems. Now we can look into the third problem. Consider scale X of a hydrodynamic and thermal entrance regions of a parallel plate channel with spacing D and a fluid with Prandtl number approximately equal to 1. Show that the scale can also be written as X by D times the Bayesian number, square root of the Bayesian number. So Bayesian number is given as the pressure drop multiplied by the diameter squared divided by thermal diffusivity multiplied by the dynamic viscosity, and delta P is the pressure drop along the X. I'll try to solve it, and I'll also try to solve it within a couple of minutes. Consider scale x of the hydrodynamic and thermal entrance region of a parallel plate with spacing d and a fluid with Prandtl number equal to 1. We have to show that the scale can be written in the form of x by d of uh, a Bayesian number raised to 1 by 2. So it's a hydrodynamic entry length problem. For this case, we can write the hydrodynamic entry length is of the order of thermal entry length. Could be written as the diameter multiplied by the Reynolds number 2. So this is already shown to the scaling. So this is scales. Scales are assumed to be same. Hydrodynamic and a thermal. So the Reynolds number can be written as UT divided by mu. In the X region, and in the entrance region, the shear stress can be scaled as tau divided by rho u squared. This can be scaled as Ux raised to 1 by 2 in terms of Reynolds number, Reynolds inverse of the Reynolds number rho. So this is something that we have actually seen while solving the similarity equations. So it could be in terms of the Reynolds number. So the shear stress can be represented, or the coefficient, shear stress coefficient, or the coefficient of a drag, or the drag or lift, that can be represented in terms of the square root of inverse square root of the Reynolds number. So at the entrance line, it can be scaled as Ux divided by mu. Therefore, force balance in the longitudinal direction gives a correlation between the shear stress and the pressure. So what we are supposed to find is x by d should be written in terms of the pressure. So this equation, the shear stress scaling gives in terms of shear stress. So if we can try to equate this shear stress with that of the pressure by using the force balance, we can get the pressure scale as well. So we can write tau into the x multiplied with the cross-sectional area can be scaled as diameter into delta P. So the pressure of the fluid in the flow direction multiplied by the cross-sectional area, that is can be plus pi by 4 into d squared, can be scaled as the shear stress multiplied by the surface area, not the cross-sectional area. That will be 2 pi r, or d times can be scaled as d times the length. So both the length and the so that length can be scaled by x, and the diameter will be there. That will be cancelled by this diameters. Therefore, the pressure can be scaled as the shear stress can be scaled as delta Pt divided by x. Therefore, therefore we have actually 1, 3, 4. So we have actually 4 equations, and we try to represent. Therefore, the shear stress it can be written as tau is equal to delta P dt divided by x. Substituting in tau, we'll get delta Pt divided by x, delta Pt divided by x divided by rho u squared can be written as nu ux divided by 1 by 2. From this, we had removed the tau. Now, if we can remove the velocity, in this bit of unknowns that are available, So if you want to represent x by d, if you have to represent this in terms of the Bayesian number has delta p d divided by alpha nu. Uh, there is one term that we need to remove, that is a u value. If we can remove the u value, everything else is available in this equation. So we can write u as in terms of x, we can write u from the first equation. So x is scaled as d into ud divided by nu. Therefore, u can be scaled as x nu divided by d squared. Substituting here, we can get delta p d divided by x nu divided by d squared into rho into u. I beg your pardon. This is equal to x nu divided by d square, the whole square. So you are substituting it for the u, and then there will be rho and x that can be scaled as nu divided by u. Again, we can actually remove here. We have to substitute it as x nu divided by d squared into x the whole power 1/2. Substituting, we can, in this given problem, Prandtl number is given as 1, approximately equal to 1. So the value of the in this particular problem, for the case of a Prandtl number approximately equal to 1, the nu can be written in terms of alpha. For Prandtl number is equal to mu by alpha. For Prandtl number approximately equal to 1, nu can be written as alpha. So what we could write is that nu can be written in the form of alpha, right? This particular term can be written as alpha. So this nu and nu gets cancelled here. Then it can be written as d by x. Here on the left hand side is delta p d divided by rho x squared nu squared divided by or alpha squared divided by d raised to 4. X gets cancelled, d gets cancelled. So that taking x and d on the right hand side, you can write it as x squared divided by d squared is of the scale of delta p d squared divided by alpha squared rho. That is x by d is of the scope order of uh, delta p d squared divided by rho. We give point is mu by nu can replace alpha. This is alpha only. This is alpha. It's alpha. Yeah, it's alpha squared. It's alpha squared. It's alpha squared. I guess there is some kind of a mistake here. So this is in terms of alpha. So that is x by d. the whole square. So x is equal to raised to 1/2. So this delta p d squared, delta p d squared divided by alpha delta p d squared divided by alpha into mu is equal to, yeah, this is alpha squared. So what we could write as one can be alpha and the other can be nu. So this is alpha squared, right? So one can be alpha and other can be nu. And we can write x by d is equal to is of the order of delta p d squared divided by this nu into rho can be written as mu divided by alpha the whole power 1/2. So this particular term delta p d squared divided by mu alpha is the same as that of the Bayesian number, and we can write x by d, that particular constant is referred to as Bayesian number dimensionless variable raised to 1/2. So that was straightforward. So we had to represent this in terms of this. For that, we use the scaling equation for the shear stress and the entrance length in terms of the diameter and the Reynolds number, and using that and equating by removing u in terms of Reynolds number and correspondingly everything else, we can actually scale the entrance length to the diameter as the root of the Bayesian number. So the original scaling was at x can be scaled as x by d can be scaled as a function of Reynolds number. So this is a bit more complicated, that tends to equate so many other parameters as well, including the pressure drop and pressure drop, Prandtl number, and the diameter of the tube as well. That completes the session for this week. So in this session, we have seen 3 numerical problems, basically derivations for slug flow, and then Hagen-Poiseuille flow with viscous dissipation, and a problem using the Bayesian number for the thermal entrance region and hydrodynamic entrance region. So these problems will help you to solve this solve the tutorial as well as the assignment problems, and then the basic assignment problems, which are multiple choice questions, are kind of easy that you could follow, but these kind of problems will help you to solve the final exams questions suitably. Next week we will actually start touching about the natural convection. If you have any questions, you can post them in the forum that is available. Thank you.